Okay. So now we're actually ready to the main part of this lecture, and that's Lebesgue integral. But what we'll do again, we are going to kind of postpone things. So the first thing we're going to do, and that's kind of the main work that we need to do, is to define a Lebesgue integral for non-negative measurable functions. So non-negative functions in particular. So we want to kind of initially avoid the pluses and minuses canceling each other. So we're only going to define the Lebesgue integral for non-negative functions. But the point is that what we'll see, what we'll define, essentially, when you stick to non-negative functions and you ask which functions are integrable, Lebesgue integrable, not necessarily Riemann integrable, it turns out that measurability suffices, right? So a measurable function, namely one that takes any measurable, whose the preimage of every measurable set is measurable, is automatically integrable. That's crazy. That means that everything is essentially integrable. And once we will move to non-negative functions, we're only going to add a small technicality to handle that. So essentially speaking, integrability and measurability is the same thing. That's actually formally true when you talk about non-negative functions, but when you talk about negative, possibly functions that attain negative values, you do need to be slightly more careful, and we'll do that. Okay. So let's look at a measure space, X, A, mu, right? X and A is the measurable part, and mu is the measure. And for a set A in A, just a measurable set, a set in the sigma algebra, we define the Lebesgue integral of the corresponding characteristic function as you expect and as we did in the example. So we define this thing, right? This symbol, it's a kind of symbol thingy. You put the integral, you put the x. Sometimes you just omit the x, but you put the x, definitely today. And then you have this d, that's just part of the symbol, right? Here you put the measure, and here you put the function that you care about. This at this point only characteristic functions. So the integral of this characteristic function is defined to be the measure of the set A. Okay. And note that it could be the case that you'll get an infinity, right? Because it could be the case that A has measure infinity, and that's fine. We will be happy with working with integrals that are infinite. I mean, I don't know if you are happy about it, but you need to carry this through even if you only care about finite integrals, okay? You will see. So sometimes you have convergence and you're not sure where series converge, and so you have to keep the option in mind that it may diverge to infinity and so forth, but never mind. Okay, so this is the definition of the Lebesgue integral for the simplest possible function, a characteristic function, which is essentially a set. Let's extend it a bit. So again, let's say you have a measurable space, a measurable map. So what is a measurable map? It's a function from X, from your set underlying the measure space, to the reals. But again, when you talk about measurable map, you need to put measurable sets on the domain, and we always mean, when you write R, we always mean the Borel sigma algebra. And let me throw in the fact that we are looking at this measure, but it's not important at this point, the Lebesgue measure. So a measurable map is called simple essentially if its image is finite, okay? But you can actually be slightly more explicit about it and say that equivalently you can write it like that. So a function is simple if there is a finitely many characteristic functions, right? So these are the corresponding those to the sets AI. AI are supposed to be measurable. I didn't write it, but AI is always in A, which is measurable. And also scaled by these CIs, which may be negative. CI is a real number, okay? So essentially a simple function, maybe I have a picture here, right? So a simple function looks like that, right? This is a simple function, which is like C1 times 3 of A1 plus C2 times 3 of A2. it's just like that. It could be also negative in the general definition of a simple function. And S plus is going to be the set of all simple functions which are non-negative. So put differently, it's exactly those functions that you can write as a combination like that, where CI's are non-negative and these are in the sigma algebra. Okay. So the next thing we are going to do is to define the Lebesgue integral for simple non-negative functions for S plus, and we're going to do it in the obvious way, right? So if you give me a function like that, a simple non-negative function, then the Lebesgue integral of that function, when you write it like that, is equal to exactly what you think it is. You just sum up the CI times the corresponding measure, like mu of AI. And again, note that this is a number between 0, it potentially can be 0, and also infinity, because some of the mui's can be infinity. And also note you have no issues with infinity minus infinity, because the CI's are non-negative, and the mu, of course, is always non-negative. Okay, the CI's are non-negative because we are working with f, which is in S plus. So now I have defined the big integral for a larger class of functions, not just for characteristic functions, but for non-negative simple functions. And you can list a whole bunch of properties. I can continue on and on here. And just to give you a taste, if you take two simple functions, non-negative simple functions, then also the linear combinations with coefficients being a negative, of course, because you want to remain in S plus. You're going to have this equality, so the integral of the linear combination is the linear combination of the integrals. Again, you are working in a cone, not in a linear space, because alpha and beta are non-negative and so forth, but okay. And you have all kinds of other properties like monotonicity. For example, if f is smaller or equal than g almost everywhere, then the integrals are respect this ordering, right? It's kind of obvious if f is smaller or equal than g, period. But when it happens almost everywhere, really the only difference is something which has a zero. The integral of that difference is 0, so you don't even see it, and you get the inequality. And of course, it also holds with equality. So if you have equality on both sides, both here and here. And you have other stuff. So the function has a measure 0 almost everywhere is the same as saying that the integral of that function in S plus is 0, and so forth. There are many properties like that that I may use without even noticing. So I'm trying not to overlook those basic properties. Now, I do want now to move on to talk about the Lebesgue integral for general functions, not negative, but other than that, general functions, like measurable functions. That's what I mean by general. Or maybe I should have said, it's kind of obvious, but I should have said that this is indeed a measurable function, right? So a simple function is measurable because it's a finite sum of measurable functions. Okay, and we said that measurable functions are closed under finite sums. So I should have said that before. Anyhow, we would want to define the Lebesgue measure for general non-negative measurable functions, not just simple functions. And we are going to need a slight technical extension here. So our functions so far were from some abstract measurable space. So X was the set of kind of points and AY was the sigma algebra. But so the function was from X, but we always had in mind the sigma algebra associated with X. And it was to the reals, right, with the Borel sigma algebra. But we will need to also include infinities, okay? So we are going to consider now functions that maps an abstract set X to the reals bar, and the reals bar mean the reals, where you join to it a plus two symbols, a plus infinity and a minus infinity. Okay. So set theoretically, that's fine. You know, that's the set, no problem. But I want to talk about measurability of the function. And when we talk about measurability, you need measurable spaces on both ends, right? Both on X side and on the range side, right? So I need to define the measurable set, the sigma algebra here. It's not going to be the Borel sigma algebra because the Borel sigma algebra is only for the reals and it doesn't include these weird plus minus infinity symbols. So we need to define those. We need to define the sigma algebra for that set. And you know, before doing that, you may say, you know, why are you doing that? You can just what you usually do? Usually, what you do is you restrict your domain if you have a function, and it maybe attains infinite values like poles. Then sometimes what you do is you just restrict to the domain, maybe to a subset of X for which F does not attain those poles and so forth. We wouldn't like to change X because X is going to be abstract, and we don't want to worry too much about that. It's easier for us to kind of alter the sigma algebra on the reals, like just add two elements and define the sigma algebra, then change kind of a weird abstract set X with its corresponding sigma algebra. Okay, so that's why we're choosing this path. It's going to serve us better. So how would you define the measurable? I don't care about the measure, just about the measurable sets. So the measurable sets are going to be denoted by this set, by this notation. It's actually not the standard notation, just notation I like. Not sure what is the standard notation here. So it's like the Borel for the reals, but it's the Borel for the reals with the closure sign here. And but that's just a notation. So this is going to include all the measurable sets. And who are the measurable sets? So a set A is going to be deemed measurable if when you ignore the plus and minus, namely you intersect the set with the reals, it should be, you get a measurable set. Okay? So what we do is we kind of turn a blind eye for measurability's sake on the plus and minus infinity. We ignore those and we just ask, you know, without those, is this set measurable with respect to the Borel sigma algebra? And if so, the set we get is measurable. Okay. Now we will also need to it's kind of again the technicality on the technicality. We will sometimes only want to consider like adding only infinity because we are going to work with non-negative functions. Only infinity and not minus infinity. In particular, we are going to consider only what we call R plus bar, which is a highly non-standard notation, I think. So it's all the non-negative reals, including the symbol infinity. So I also write it like that. And we define the corresponding Borel measure as you would imagine. You just ignore the infinity and ask whether the set is in the sigma algebra, in the Borel sigma algebra. Okay. So with this, we're actually ready for the main definition. Okay. So say a measurable function f from x. Now I equipped it also with the measure mu. Okay, so it's not just a measurable space; it's a measure space. To R plus bar. So that's again what we said before. So this is the this set equipped with the adapted Borel measure, Borel sigma algebra, namely the sigma algebra that ignores infinity for the purpose of determining measurability. So say you have a function like that. So it's essentially a measurable function. That's it, right? So we define the integral of f on x with against the measure mu as the supremum over all simple non-negative functions below f. of the integral value of that. So you take any possible simple function that still goes below f, right? And for those, we defined this integral, which may be infinite, but it's a number or infinity, so it's not ill-defined, right? The supremum of that, which may be infinity, so it's a number here, is our definition for the integral of f. And f is called mu integrable or mu Lebesgue integrable, but everything is going to be Lebesgue integrable here. If this integral turns out to be finite, okay? So we work with infinities all the time because we kind of need to for developing the theory and also for some of the theorems, but a function is deemed integrable if it is, first of all, measurable, and secondly, this supremum, this value, is some finite number. So a word about Riemann versus Lebesgue's philosophy about these things. So if you remember, I don't know if you remember, it was probably a long time ago, but when you talked about Riemann's integrals, you had this curve somewhere or something like that. And in order to define the integral, you kind of took partitions, like finer and finer partitions of the real axis. And then you kind of looked at, you know, the corresponding function that goes below and also above, but never mind that now, of the Riemann, of the curve. And you defined the integral to be the supremum of overall finer and finer partitions, the supremum of the corresponding areas, and the infimum of the areas that close over it. And the integral was defined if the supremum was equal to the infimum and so forth. But the point was that you considered finer and finer partitions of the x-axis, right? Lebesgue, on the other hand, and I'm a big fan of Riemann, but here Lebesgue is completely one. So Lebesgue, on the other hand, considered a different kind of partitioning. And actually, even before doing that, when you consider like maybe you know, the two-dimensional curves, not curves, surfaces, manifolds, I don't know. These are not the right names anyhow, but you know what I mean, something like that. Then what you did, you kind of had to say, oh, now it's kind of more annoying. Now I have to partition the plane that sits below, or maybe not below, but you know, sits below this manifold. And then you consider smaller and smaller partitions like that, and so forth. It was a headache at some point, because when you go to higher dimensions, you can't really see what's happening. And Lebesgue, on the other hand, said, you know, the only thing that doesn't change is the real axis, the y-axis. So it's actually better to partition the y-axis and not the x-axis. And according to that, take the partitions. So at the most abstract setting, in our case, right? So x is, you know, there is no, it's not a, you don't have, so it's not a metric space. You're not going to do these small absolute values and so forth. It's an abstract space. It's a measurable space. We are measure, but it's an abstract space. So it's harder to kind of make finer and finer partitions of it. I mean, it's harder to work with that. I mean, you can define that, but it's harder to work with that. So what Lebesgue did was actually to consider partitioning the y-axis, which is just the reals, right? Also equipped with the Borel sigma algebra, but just the reals. And so the point being, right, so the way we define it, so we take any curve and we take the supremum of all possible simple functions, right? Maybe that's one simple function, h, a non-negative simple function that sits below your curve, and we can consider like a higher one, maybe like that, and so forth. But you can actually get those functions in a natural way by considering partitions of the y-axis. Right. So for example, in this partition, for example, if you look at this kind of partition they have, I kind of so you can look at these two this part between these two, and you can consider this h function, right? That kind of goes below the highest one that goes below the graph. And right, so refining the partitioning in the y-axis has the same effect essentially as taking the supremum of all step function, all simple function, non-negative simple function below the curve. So the Riemann versus Lebesgue philosophy is to actually do the partitioning on the image and not in the range and not in the domain and so forth. But anyhow, it doesn't really matter. And note that when you do that, you need these things to be right. When you do that, you need these sets to be. These are the measurable sets that you care about, and that's why the Lebesgue, the Borel sigma algebra is important, because these sets are measurable. So the pre-image of them is a measurable set. But I don't think I'm explaining it too well, and anyhow, it's not that important for now. Okay. Maybe let's take a short break and we'll continue afterwards.